Hi, math students. Today's lesson is going to focus on the concept of continuity of functions. It's a really simple concept. I think you studied it in pre-calc, so this would just be a bit of a review. Let's start here with the definition of continuity. So I'm just going to read it out loud to you. Definition: continuity at a number. A function f is continuous at a number c if the following three conditions are met. Number one, f of c is defined. Number two, the limit as x approaches c of f of x exists. And number three, the limit as x approaches c of f of x is equal to f of c, which is basically saying that the first two conditions are equal. If you can prove these three bullets for any function or any graph, then you have proved continuity. Now, the informal definition of continuity is so simple. Basically, I'll write this down. If you can trace a graph without, I'll capitalize that, without lifting your pencil, then the function which makes that graph is continuous. So these hiccups we've been talking about in previous lessons, the vertical asymptotes, the holes, those are hiccups on your graph. So those are values of x where we would be discontinuous or not continuous, because you know whenever you hit a hiccup, you have to pick up your pencil. So let's get into it here. Let's take a look at example 1. It says, is the function graph below continuous at x equals 3? Okay, so in our definition, we see this c value. Whatever x value you're testing, that's your c value. So when we run through the definition, everywhere we see a c, we're going to replace it with a 3. Okay, so let's do our first bullet. The first bullet says f of c must be defined. So let's do f of 3. Okay, well, f of 3 is the y value when x is 3. So let's go to x equals 3. 1, 2, 3. It looks like, boy, these are really, looks like that's 1, that's 2. This looks like 3. So I'm going to go with f of 3 equals 1. So that checks out. F of 3 is defined and it's equal to 1. There is a dot, a filled in dot, when x is 3. Okay, let's do our next bullet. The limit as x approaches 3 of my function f of x. Okay, well, we know when we're doing a limit from a graph, we test out the right and the left, and we make sure that both sides have y values coming toward the same value, which in this case you can clearly see is 1. So I'm going to say that the limit exists and is 1. And now the third bullet is, do these two match? Does 1 equal 1? Well, yes, it does. So we'll say the limit as x approaches 3 of f of x is equal to f of 3, and they're both equal to 1. Therefore, this is my little notation for therefore, f of x is continuous at x equals 3. And if you informally look at it, if you were tracing this graph, you would definitely not have to pick up your pencil as you came through x equals 3. It just flows very nicely. It's that simple. Okay, let's go to the next one. Example 2. Is the function graph below continuous at x equals 2? Okay, well, x equals 2. 2 will be my c value in the definition. So let's take a look. Bullet number 1. We have to find f of 2. So let's go to the graph. F of 2 is the exact y value when x is 2, which is this filled in dot up here at 4. So f of 2 is 4. Second bullet, we must find the limit as x approaches 2 of f of x. Okay, the limit. Where are the y values headed as we come in toward 2 from the left and the right? So if we get on the function here, it looks to me as if those values are coming to 2. Again, we can have a limit on either side of a hole because f of 2 can be up here somewhere different. Okay, last bullet. Do they equal each other? Well, you can see here they do not. 4 and 2 are not the same. So I'm going to say that the limit as x approaches 2 of f of x does not equal f of 2. And because step 3 fails in the definition, we state, therefore, f of x is not continuous at x equals 2. You can also say discontinuous. Okay, so let's look at the informal definition, the tracing. So if you were tracing from left to right, you would trace, 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 trace. You come to the hole, lift your pencil, fill in this dot, come back down, trace, 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 trace. So we definitely did have to lift our pencil, and therefore not continuous at x equals 2. Okay, on to example 3. Is the function graph below continuous at x equals 2? So x equals 2. 2 is our c. Here we go. First bullet, f of 2. Let's see if we can find that. So let's go to x equals 2. Where are we filled in? Right here. Y is 4. So when x is 2, y is 4. Step 2 is the limit as x approaches 2 of f of x. And the limit as x approaches 2, well, from the left, we're going to 4. From the right, we're headed to 6. So since the limit from the right does not equal the limit from the left, we know to say that this limit does not exist. Okay, so since step 2 fails, we didn't even get a real number here. I can stop right there because step 2 said that the limit had to exist. This does not exist. So I'm just going to say, therefore, f of x is not continuous at x equals 2. Informal definition, tracing, 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 tracing. When we get to 2, we have to stop, pick up the pencil, and then start tracing on another function. This is piecewise. Okay, fantastic. Example 4. Is the function graph below continuous at x equals -2? So we change our c this time to -2. So let's start with our first bullet, f of -2. All right, let's go to -2. If you go to x equals -2 and you search down and up for the y value, there isn't one. This is a hole. So f of -2 does not exist. So we're done because the first step says it has to be defined. F of -2 is not defined, so we're done. Therefore, f of x is not continuous at x equals -2. Again, if we were tracing, trace, 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 stop, lift, trace, 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 and on your merry way. So you have to lift your pencil up at that hole. Hiccup. Hiccups are not continuous. Okay, so what happens in examples 5 and 6? Like if we're not given a graph? Well, it's basically the same thing. You just want to do your limits and your f ofs analytically by hand. So example 5 says determine whether f of x equals 3x squared minus 5x plus 4, whether that is continuous at 1. So 1 becomes our c value. Now I can tell you just from doing this for a lot of years, this is quadratic, okay? Quadratics. I know quadratics are continuous everywhere. So I never have to lift my pencil when I'm drawing a parabola. So I'm gonna go ahead and venture a guess that this is continuous. But to prove it with the definition, I'll have to run my 3 steps. So I'll start with the first step, f of 1. And I just show that work. So f of 1 is equal to 3 times 1 squared minus 5 times 1 plus 4. And that is going to be 3 minus 5 is -2 plus 4 is 2. So we are defined. F of 1 is defined. Next bullet is the limit as x approaches 1 of the function 3x squared minus 5x plus 4. Well, we know to do a limit analytically, the first step is just to plug it in. So I'm just going to plug it in. 3 times 1 squared minus 5 times 1 plus 4. and that's also 2. So f of 1 is 2. The limit as x approaches 1 is 2. They're equal, so I'll state that the limit as x approaches 1 of 3x squared minus 5x plus 4 is equal to f of 1, and they both equal 2. Therefore, I conclude that my function f of x is continuous at x equals 1. So this is just saying informally that if I draw this quadratic, when I get to x equals 1, I don't have to lift up my pencil, which is exactly what I guessed. All right, now, example 6. Determine whether g of x equals x squared plus 9 over x squared minus 4 is continuous at x equals 2. So there's my c. Now this one, I'm a little bit more worried about this. It's a rational function, and we've studied the fact that rational functions have hiccups. They have vertical asymptotes, they have horizontal asymptotes, they have holes. So this one has way more potential of being discontinuous than my quadratic. So I'm really going to have to be careful here. So let's start in with the first step. F of 2, let's plug it in here, is going to be 2 squared plus 9 divided by 2 squared minus 4. And this is going to give me 13 over 0, which is undefined. And we know that the first bullet has to be defined. So there's a hiccup already. So I'm going to right away just conclude that f of x is not continuous at x equals 2. In fact, there's a vertical asymptote there. So so wherever this graph looks like at x equals 2, there's a vertical asymptote. So no matter which way this graph goes, which I could do more work to graph it, but let's just say, you know, the graph goes up, the graph goes down. I have no idea, but I'm just guessing. If you were tracing, you would have to come in, lift, trace. So you definitely have to lift your pencil over that vertical asymptote. So we're not continuous there. So that's your lesson on continuity. Not terribly difficult to understand, but you do have to follow this recipe to determine if you have continuity.